Welcome friends, Igor is here, and in this video we will discuss the notions of linear dependence and linear independence. In this lesson we will define the notions of linear dependence and linear independence for column vectors and discover that these properties are related to solutions of homogeneous linear systems. Let's get started. First, we will define relations of linear dependence on the set of column vectors. Given a set of column vectors of the same size, a true equality of the form where a linear combination of these given vectors is equal to the zero vector is called a relation of linear dependence on this set. If this equality is formed in a trivial fashion, namely all scalars are equal to zero, then we will call this a trivial relation of linear dependence. The reason we call this relation trivial is because it is always there. If you take any set of column vectors, it always has a trivial relation of linear dependence, because if you use zeros for scalars in a linear combination of these vectors, it is always going to equal the zero vector. It doesn't matter what the original vectors are. Now we are ready for the main definition of this lesson. A set of vectors of the same size is linearly independent if the only relation of linear dependence on this set is the trivial relation of linear dependence. If there is a non-trivial relation of linear dependence, then this set is called linearly dependent. So, every set of vectors is either linearly dependent or linearly independent. Let's see how we can decide if a given set of vectors is linearly dependent or linearly independent. We start with the first example where we take a set of 4 vectors of size 5. To determine if this set is linearly dependent or independent, we need to look at the possible relations of linear dependence, and therefore we start by constructing such a relation of linear dependence. Keep in mind that this vector equation always has at least one solution, the trivial solution where all scalars are equal to zero. For this reason, we call this the trivial relation of linear dependence. So the real question is not whether this vector equation has a solution in terms of the scalars. The question is, are there any non-trivial solutions? Once again, let's use the fact we established earlier that solutions to such vector equations are exactly the solutions to linear systems, where the vectors from the left-hand side are used as columns in the coefficient matrix, and the vector on the right-hand side is used as a vector of constants. This means we're looking at solutions of the homogeneous linear system where the coefficient matrix is constructed by using the given vectors as columns. To solve the homogeneous linear system, we reduce this coefficient matrix, and we see that we have 3 pivot columns and 1 non-pivot column. This means that there are infinitely many solutions of the homogeneous linear system because the variable x4 is a free variable. But now, because there are infinitely many solutions to the homogeneous linear system, some of those solutions are non-trivial. We can construct specific non-trivial solutions by assigning non-zero values to the free variable. For example, let's assign a value of 1 to x4. This gives us a particular solution to the homogeneous linear system, and it is non-trivial because at least one value, x4, is not equal to 0. But now, because this is a solution to the homogeneous linear system, it is also a solution to the corresponding vector equation, where the vectors on the left-hand side are the columns of the coefficient matrix. This tells us that there is a non-trivial relation of linear dependence on the vectors of the set T, and in turn, this means that the set T is a linearly dependent set. Let's look at another example. We take a set of 4 vectors of size 5, and again we need to figure out if this set is linearly dependent or linearly independent. For this, we start by constructing a relation of linear dependence on this set. Once again, we don't forget to keep in mind that this vector equation always has the trivial solution, and the real question is, do we have any non-trivial solutions? If there are any non-trivial solutions, then the set of vectors will be linearly dependent, and if there are no non-trivial solutions, if there is only the trivial solution, then the set of vectors is going to be linearly independent. Similarly to the first example, we use the given vectors to construct the coefficient matrix, and we look at solutions of the corresponding homogeneous linear system. We reduce the coefficient matrix, and now we see that every column is a pivot column, every variable is a dependent variable, and there are no free variables. This means the homogeneous linear system with this matrix as the coefficient matrix has only the trivial solution. And therefore, there is only the trivial relation of linear dependence on the set T. This means this set T of vectors is linearly independent. Let's formalize our findings from these two examples in the general theorem. Suppose we have a matrix and we consider the set of vectors which are the columns of this matrix. Then this set is linearly independent if and only if the homogeneous linear system with this matrix as the coefficient matrix has a unique solution. This is an if and only if statement, and it means there are two separate implications for us to prove. In one direction, we are going to assume that the homogeneous linear system has a unique solution. Then we need to prove that this forces the columns of the matrix A to be linearly independent. We have a homogeneous linear system, and if it has a unique solution, it must be the trivial solution. But relations of linear dependence on the columns of the matrix A are the solutions of the homogeneous linear system. So in turn, this tells us that the only relation of linear dependence on the set of the columns of the matrix is the trivial relation. By the definition of linear independence, this means the set of the columns of the matrix A is a linearly independent set. In the other direction, we are going to assume that the set of columns of the matrix is a linearly independent set. We need to prove that this forces the homogeneous linear system to have a unique solution. In this case, we will use proof by contradiction. So we have our assumption that the set of columns of the matrix A is a linearly independent set, but we are going to assume the opposite of our desired conclusion. Namely, we are going to assume that the homogeneous linear system with A as the coefficient matrix does not have a unique solution. But if a homogeneous linear system does not have a unique solution, it means it has infinitely many solutions. Because homogeneous linear systems are always consistent, they always have at least one solution. Infinitely many solutions means there are non-trivial solutions. And such a non-trivial solution is going to result in a non-trivial relation of linear dependence on the columns of the matrix. In turn, this means that the columns of the matrix A form a linearly dependent set. But this is a contradiction with our assumption that the set of the columns of the matrix is linearly independent. Set T cannot be both linearly independent and linearly dependent. What was the source of this contradiction? Well, this contradiction was caused by our assumption that the linear system with A as the coefficient matrix, the homogeneous system, does not have a unique solution. Therefore, this assumption leads to nonsense. It cannot be true. This means the homogeneous linear system with A as the coefficient matrix must have a unique solution. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see future videos. In the next video in this series, we will discuss properties of linearly independent sets of vectors. I will see you later.